Starting from this video, we will look at the error backpropagation, which is the third topic of deep learning. In this video, part 1 of a series on the backpropagation, we will look at the backpropagation along single path. This video was produced in Korean and translated into English. My voice was generated by AI text-to-speech. Let's take a look at the full table of contents. In the first video, we will look at the error backpropagation on a single path. Let's look at how backpropagation works through a simple example and interpret the results. In the second video, we will look at error backpropagation along multiple paths. We will then look at activation functions and the vanishing gradient problem. We will also learn about numerical differentiation and automatic differentiation methods for differentiating the activation functions. In the third video, we will take a closer look at automatic differentiation. In the artificial neural network series, the neural network was approximately implemented using numerical differentiation. However, in order to accurately implement a neural network, automatic differentiation must be used. In this series, we will take a closer look at how automatic differentiation works. Automatic differentiation methods include forward derivative trace and backward derivative trace. Let's look at both methods and see which one is better. And let's look at how to perform automatic differentiation in TensorFlow. Let's look at the process of error backpropagation along a single path. Let's take the simple neural network below as an example. This is a multi-layered perceptron consisting of an input layer, a hidden layer, and an output layer. And each layer has only one neuron. The lower and upper neurons are connected with one weight W. Let's see how the error propagates backwards through this network. Data point x1 is input to the input neuron, and x1 is input as is to the hidden neuron. The connection weight between the input neuron and the hidden neuron is W1. The hidden neuron calculates x1 times W1 plus bias B1 to generate Z1. And this neuron uses the activation function F1 to transform Z1 into X2 and outputs X2. Here we will use the ReU activation function. The output of the hidden neuron, X2, is passed to the output neuron. The connection weight between the hidden neuron and the output neuron is W2. The output neuron calculates X2 times W2 plus bias B2 to generate Z2. And this neuron uses the activation function F2 to transform Z2 to Y hat and outputs Y hat. Here we will use the linear activation function. Let's use mean squared error as the loss function. Y hat is the output value of the neural network. And Y is the desired output value. Since Y is known, it is easy to find the error by Y hat minus Y in the output layer. First, let's update W2, the weight of the output layer. We can update W2 using gradient descent like this. To differentiate the loss L with respect to W2, we apply the chain rule as shown below. The reason we need a chain rule like this is because the loss L is a function of Y hat, and Y hat is a function of Z2, and Z2 is a function of W2. Differentiating the loss L with respect to Y hat gives Y hat minus Y. This is the error. The differentiation of Y hat with respect to Z2 can be written like this. And differentiating Z2 with respect to W2 gives X2. Let's update W2 using the example on the right. Let's assume that the initial value of W1 and W2 of this network are both 0.5. And let's assume that the biases are all 0. Data point 1.0 is input into this neural network. Then the output y hat will be 0.25. If the desired output value y is 1, the loss will be 0.2813. The derivative of L with respect to y hat is negative 0.75. And since f2 is a linear function, the value of its differentiation with respect to z2 is 1. Finally, the derivative of z2 with respect to w2 is x2, which is 0.5. Therefore, this formula updates w2 from 0.5 to 0.5375. Here, the learning rate alpha is set to 0.1. Next, let's look at the process of updating the connection weight W1 of the hidden layer. By gradient descent, W1 is updated as follows. To differentiate the loss L with respect to W1, we apply the chain rule as follows. Starting from the output layer and going down to lower layer, we calculate the gradient of the loss L with respect to W1. The chain rule is applied iteratively to calculate the gradient of the loss L. That way, the gradient propagates backwards through the network. This is forward propagation path. And this is backpropagation path. Forward propagation is for calculating the output value of the neural network. And backpropagation is for updating the parameters of each layer. We'll take a closer look at how errors propagate backwards on the last page. Now let's update W1 in the example on the right. Each derivative in the chain left is as follows. The first derivative in the chain is the error, which is negative 0.75. The second one is 1 because f2 is a linear function. The third one is w2, so 0.5375, updated from the previous page. The fourth one is 1 because f1 is ReLU and z1 is positive. The last one is the input value x1 1.0. Using these values in the formula on the left updates W1 to 0.5403. So far, W1 and W2 have been updated once. The biases B1 and B2 have not been updated yet. The biases are also updated in the same way as W, using gradient descent and the chain rule. Let's compare the neural network before and after W is updated. The output value before updating W is 0.25, and the loss value is 0.2813. The output value after updating W is 0.2904, and the loss value is 0.2518. The loss value has become smaller. And the output value of the neural network got a little closer to the desired output value of 1.0. By iteratively updating W and B in this way, the loss value gradually reaches a local minimum. And the output value of the neural network becomes increasingly closer to the desired output value. This is the training process of a neural network using gradient descent and backpropagation. Next, let's interpret the meaning of the backpropagation process in detail. The gradient of loss L is broken down into 3 parts by chain rule like this. A large gradient with respect to W2 means that W2 is far from the minimum point of loss L. This means that the W2 value is significantly wrong. So W2 needs to be updated a lot. This is what gradient descent means. This time, we will look at the meaning of each derivative in the chain. The larger the magnitude of each derivative, the more W2 is updated. The first derivative in the chain represents the error of the neural network. If error is 0, then W2 will not be updated. This means that if the output value y hat of the neural network is the same as the desired output y, then current W2 is correct and will not be updated. The third derivative in the chain, x2, is the output value of the hidden neuron and the input of the output neuron. If this is 0, the connection weight W2 between the two neurons will not be updated. This is because the hidden neuron did not contribute at all to the output neuron outputting an incorrect result. Finally, the second derivative in the chain is the derivative of the activation function f2 of the output layer. The derivative of f2 tells you the output sensitivity to change with respect to a change in its input, z2. If z2 changes slightly, but the output changes significantly, the stability of this network decreases. Therefore, if w is at the point where the derivative of f2 is large, it is better to change w significantly in order to quickly escape from this point. For example, if f2 is sigmoid and z2 is 0, the derivative of f2 has a maximum value of 0.25, and f2 becomes 0.5. If this output is used for binary classification, the output 0.5 will not help at all. In binary classification, the closer the output value is to 0 or 1, the better. Therefore, the larger the derivative of f2, the more updated W2 is. If the error of the output layer is E2, the formula for updating W2 can be written as follows. Next, let's look at the process of updating the parameters of the hidden layer. The gradient of loss L is broken down into 5 parts by chain rule like this. This equation can be written as follows. Here, let's define this part as E1. Then the expression that updates W1 can be written as follows. This expression has the same form as the expression that updates W2. Since E2 is the error of the output layer, it can be inferred that E1 is the error of the hidden layer. Since the desired output y is known in the output layer, the error can be easily calculated as y hat minus y. However, the desired output value from the hidden layer is unknown. If the desired output value is h, the error of the hidden layer can be calculated by subtracting h from x2. But since h is not known, the error cannot be calculated directly. However, even without knowing h, we can see that E1 corresponds to the error of the hidden layer. This allows us to update W1 with gradient descent using E1 as a proxy for the error in the hidden layer. This is what the expression that updates W1 means. W1 is responsible for this amount of error. The remaining F1' and X1 parts have the same meaning as the output layer. In other words, the error in the output layer is backpropagated, and the error E1 is assigned to the hidden neuron. This is the error backpropagation algorithm. So far, we have looked at the process of updating parameters through backpropagation on a single path. In the next video, we will look at backpropagation along multiple paths.